more or less down the road to JPL, where
Up the hill.
did quite a bit of work along the lines that he's been doing lately at University of Connecticut in the Department of Mechanical Engineering. For those of us working on the climate model here, George is involved in currently, for instance, in an NSF NOAA climate process team working on CESM development that is working on extending CLUB to a fully unified scheme. So I will say that George's work is both technically excellent and also beautiful. So
thank you. So I don't
without
know
further ado,
they're technically excellent, but
yes,
we do claim to be beautiful. All right. Okay. So thank you, Juan. Thank you for having me here. It's great to be here. It's we're close by. So if you guys want to, I don't know, like take the train and come up the coast a little bit, like we're close by, we'll happy to host you and hang out.
I thought you were in the woods. You're not on the coast.
So this is what the campus is actually in the woods in a little area. So I don't live there, but some people like it. It's a matter of preference.
It's nice.
You see. Anyway, so come on, computer.
Is that stores then?
Yeah. So the campus.
It shows it choosing the right app.
All right. Okay. So the campus is in stores. It's kind of like in the eastern part of the state. I live close to Hartford. It's a little bit more suburbia because I've been in Pasadena, Los Angeles for a long time before coming here on the East Coast, and it's I had trouble kind of like telling my family, hey, now we're gonna go from Pasadena in the woods, with nobody. So we ended up in suburbia. Okay, so I want to thank NSF for funding this work. This work we do through the CPT for convection, and everybody else at CPT. There's many people at NCARB, GFDL that we interact with them very, very often as part of this. I'm going to show you some big runs we did. We ran the big stuff on Cheyenne. It's NCARB's computer. And we have like a smaller computer at UConn. I'm gonna talk about a couple of the work is mainly done by my student Umayma Lamakel. She's getting ready to graduate now. So this is essentially her work, her PhD thesis. I'm a little bit like just the messenger here. I'm here to most likely she did the work. I'm here to entertain you. Okay. So there's a couple of papers. One of them is basically finished. I can send it to you if you are interested. One of my goal is to more have like a discussion today. So I'm not going to go into all the details. I'm going to talk about a few things. I have basically like 3 parts. If we don't get to the third, you want to stop on the first one, it's okay. No problem, right? You guys feel free to interrupt. We can chat whatever you guys want to do. Okay. Before we go into like the details and things like that, because we're at the university, we have sort of like our first goal is to educate people, to inform them, right? Not only for our students, but also like the general public. So we have we have a website at the university. We have another website that we post like education outreach pictures, things like that. You can get computer code data. If you're into more like social media, we post some stuff usually on Twitter. You don't need to sign up on the thing. You can just go on the webpage and look at stuff. If you guys have interesting things and you want to, I know that you're in a more like if you're at NASA, you're in a more controlled environment. But if you have some interesting ideas, you want some, you have some visuals you want to share, just let us know. We can do something. We can post stuff on the website like it's if you want to tell the public about your simulations through our channels, happy to do that. Okay, so usually when I do this, when I have to present a little bit of my work, I start by telling people about climate. I show them maybe some flaws from the IPCC, things like that. I was going to do that actually coming here, but then I thought about this and that is a little bit ridiculous if I come here and show you explain to you your plots, right? So I'm not going to do that. We're going to do something a little bit different. a little bit more educational if you want. And I decided to talk about LES and high resolution modeling because that's what I do most of the time. So maybe I know a little bit about the subject. So whatever I know, I'm going to share it with you. Okay. So we're going to go through the first part, which is like the introduction. Most of the work I'm going to do, everything I'm going to talk about has to do with turbulence. There's more stuff out there. There's like microphysics radiation, all of these things, like ice sheets, ocean. We're going to talk about turbulence basically today. So turbulence is like a big deal. It's been like this for a long time. And for all of us that we do simulations, we do stuff on the computer. This is basically where things started. This is so Richardson, exactly 101 years ago, he wrote this book, Weather Prediction by a Numerical Process. Now you take weather forecast for granted. You take your phone, you check, if there's tomorrow like a snowstorm, things like that. It was not always like this, Remember going out, you go outside, go to the next town or something to sell your stuff, to sell your cheese or whatever, right? You come back, you get caught into a blizzard, not a good situation. You don't know about that because there's no forecast, right? So this was like a societal need when Richardson was around 100 years ago. He thought about the problem, right? He wrote this book. This is a map of Europe. I don't know how well you can see that. And this is a grid. This is a computational grid. So everything you do today on your computer, he thought about this first, right? He made this is like his vision. So Richardson wrote the book, and then he went to downtown London. He went to the Apple store to buy a Mac to do the simulation. No? You guys sound like you go to the Microsoft store or something. No? Okay, this is the interesting thing. The word computer existed when Richardson was alive. It did not mean like this thing here, like the device. So a computer was a person. It was a person who was very good at doing elementary school math by today's standards, right? So his idea. So this is from his book. These are like his words, right? So he wrote this in the book. He imagined that you have all these people. This is like a little bit of like an artist rendering afterwards in a big place, all working with each other and being coordinated. So not only he envisioned weather forecast computations, he also envisioned distributed or parallel computing, as we know about this today, because he realized that one person, like one CPU, by today's standards, would not do the job, right? So, since Richardson would have come like a long way, so we are here to simulate the atmosphere for climate, for weather, for.
I just want to say, back in the previous one, that was realized, right? That is how they were doing their predictions with the whole. I mean, it wasn't maybe that architecturally designed, but.
So he actually, so like you say, he actually attempted it, and his calculation actually, nobody knows what happened. He did not. He was unsuccessful. Right? He was unsuccessful because they did not know anything about stability, about all of these things that you go today to school to learn, in American analysis, or if you take some other classes, they did not know it back then. It was like, but he tried it. He actually, that's correct. He actually attempted the calculation. It did not go very well, but
first instance of MPI.
Yeah. So okay, so we have come a long way. Now we know how to deal with equations, with math, with all these problems. Usually we cannot do like simulate the entire atmosphere. And again, I'm talking about turbulence here, about transport. I'm not talking about radiation, microphysics, more other things that they come on top of this thing. Okay, so you can do a GCM, take the entire planet, go down to how much scale your computer affords, right? And then there's a little bit, a big range here that it's like things that you're not going to explicitly resolve on the computer. Then you have to fill this range with some knowledge. Part of the knowledge comes from modeling, comes from LES. It's like the things I'm going to talk about today. There's a bit of LES part that remains unresolved. And me and my students collaborators, sometimes we do DNS to fill in this little bit of gap that LES leaves. Okay. Okay, so let me show you this. So this is so what I'm going to show you here. I'm going to do it like this. So this is actually an LES. So this is LES output. This is trade wind, like fair weather cumulus boundary layer, right? These are clouds. This is LES. We take the LES output. We pass it through this multispectral 3D radii transfer model. This is what we get. Okay. If you're a modeler, you know, we all go and talk to each other. We complain about this thing. This I don't, my code crashes, my parameterization doesn't get these, things like that. But on the other side, this is done on the computer. This is not computer graphics, like is whatever comes out of, even from the radii transfer, we did not smooth the image or anything like that. There's not a lot of light. It's grainy. Whatever comes out, it's what I'm showing you, right? And when I show this to people that are experts on radiation, they pick up things that are not fully physical, but I have never had like a regular person tell me there's something wrong with this or this. Okay, and I show this often whenever I talk with engineers and things like that, because look, today we know a lot of things. Richardson failed, but we've come a long way. We can figure out the problem, right? Problem is difficult, but we have also come a long way. So you can get things today on the computer that are basically indistinguishable from reality. Again, this is not AI, computer graphics, things like that. Everything has, like an equation. We just solve like PDEs on the computer, with either doing turbulence or radiation, things like that. This is purely.
What's the shading on the clouds? Where is it coming from?
So these are like from the backlit. So you get a lot of like
ray tracing, right?
Yeah, it's basically ray tracing. So.
This is the renderer.
This is So this is the references here. This is HD LDR. You have to say this in the French. Yeah. I'm not going to attempt that. This is a reference, so you can go check online there. Yes.
Now, there's one thing I was curious about. Are the little red speckles actually the output, or is that from the movie rendering?
No, this is the output. So I output this. The way this works is that you say, I have like this many pixels, just go do ray tracing on this many pixels. And when there's the sun is, this is the sun, okay? So when there's like a lot of light, it looks better. If the sun goes like down here, when there is not a lot of light coming in, then you need to get more samples per pixel to get rid of the noise, right? So this is like a Monte Carlo situation. So so rendering each of the frames of the video takes about 2 hours on 36 CPUs. So each of the frame actually is like a pretty significant calculation on top of like what we did with the LES.
You must be doing something with the sun, because the sun should be very bright and you can't really look at the sun like that.
Like I said before, if you're an expert, you're able to pick up things. But if you're like like
sun.
So I have a quick question from a technical standpoint.
Yeah.
Like the number of usually for something like this, we you're intentionally outputting really frequently just for a beautiful rendering. Did you actually scientifically use the 3D output at that frequency for other purposes? If you saved it that frequently, it's it's intensive.
Yeah, we had the output already. We did not like So we I don't know. We get requests all the time from people that they want data to do stuff. So this is BOMX for we ran this very long time ago. It was like a very high resolution, 10 meters, like a very high output. I don't remember. It's been like many years since we did the run. I don't remember why we did that, but we have the output.
So you might do 1 minute output. Like the only reason we do that is for thermal tracking, basically. That really frequent output, your whole 3D field is really expensive to store.
The administrator. It's been a while since we did that. But it used to be whenever the administrator would come to Ames.
This is broadcasted online, right? Okay, they are broadcasting this online, so.
have one question from Ron Miller online.
Yeah.
He says, "Why is your ocean so syrupy?" I'm not sure if I can qualify what syrupy.
Okay, so the ocean it is a little. So they have these surfaces inside their model. So one of this is we did not do it. So we selected one of the standard surface, and one of the standard is like ocean, and they made their ocean syrupy. I don't know. It's like their view of the ocean. You can make your own ocean actually, but you have to go inside the model and like have like the surface, the triangulation of the surface, and things like that, and then the relative properties of the surface, and then the radiation will do things for you.
And you really can't do this yourself. This is open source code, right?
Yeah, this is open source. It's fairly complex.
Yeah.
I interacted a lot with them. Like without their help, I don't think I could have done this myself.
I know.
Yeah, I interacted with a lot with them, so that like.
Did you win did this win an award?
Yeah. This won an award from the American Physical Society. They have this gallery of fluid motion, it's this one they have this gallery about nice pictures with fluids and things like that. But they're also like scientifically significant. So the video is online. It's on YouTube. Like if you go on, you guys can watch it.
Very nice.
We are good with the pictures.
And the radiative transfer in the model is different than what's being used for visualization.
Yeah. So in this case, there is no really radiative transfer happening inside the model, but yeah, if you see some of our cumulus pictures, the radiative transfer is different. What we have in the LES and here.
And the reason it's not in the model is because it's not very significant as a process.
Yeah, this is this is actually like I'm gonna play this. Let me do this.
Trade-wind cumulus is not very significant.
So, yeah, this is synchronized with the sun. So the time the clouds take is like with the sun angle is like we made this so that they're realistic. You can see. So these clouds they live for like half an hour. 40 minutes, like the bigger ones. So it's they are very signature on hitting or pulling. It's pretty low, and they're pretty scattered. Like okay, ready to go? Ready to go? Okay, so I do LES, and I'm gonna try to explain what is LES without saying the word tensor or writing any math. Okay, so we're gonna do a little bit of you can do the same thing with math, but we're gonna do cartoons, okay? So this is the problem with turbulence. There is stuff big and small, right? So there's big and small stuff like this googly eyes here, okay? As you can see, my googly eyes, they're all kind of like looking at each other. So it's a nonlinear problem, and you have interactions between scales, right? If you inject energy into one scale, it has a tendency of going to another scale, right? Because there's nonlinear interactions. This is important. Okay, we cannot simulate all of them, big and small. So this is what the textbook will tell you. You have to separate them, right? This is the same thing as you do in your kitchen. You have like this filter, right? In your kitchen, you separate stuff, correct? Okay, so you're going to separate the small scales. And if you see here, so this is what the textbook will say. I'm going to pass a filter and I'm going to separate the small scales. But this is still not LES, right? Because if you do this, I'm not writing any math, but if we're writing any math, then you can defilter or you can deconvolve, right? So if you don't want to be able to defilter or deconvolve, you have to coarsen. Okay, so you're going to take the small guys, you're going to swipe them away, right? You're going to toss them away. What this will do to you, it will take the big guys and it will kind of like compact them together. But at the same time, this will change even the way the big guys interact with them. Okay, and this is important because some of the small guys, they were kind of like in between here, and you remove them now. So sometimes there's like a small guy interacting with a medium guy, and it's maybe like stretching the medium guy to be a little bit bigger, right? So you are missing this stuff. So this is in the literature, this is called like backscatter, or energy transfer to like the larger scales. So if you're doing these things, you're messing up also a little bit of like the large scales, right? So this is true for any kind of modeling. You have to keep this in mind. So the model we use here, that it has like so it is able to give this backscatter, at least in theory, right? So this part is part of the model. Okay, so this is what the textbook will tell you. Unfortunately, this is not what LES is. So all this discussion we have now is just like data science stuff. So you have data, you coarsen them, you filter them, toss away some guys. So what LES is about, it's about this. Okay, so you have these guys, and they're kind of like being transported into like space-time, right? And this capsule or the spacecraft that they're being transported in is basically the Navier-Stokes equations. So you have an initial condition. This is an initial boundary value problem, right? You initialize, you put these guys inside the spacecraft, just send them, okay? So you initialize your climate model, you do the run, okay? So this is what we're actually doing. The previous stuff, this is like data things, like data manipulation. This is what we are doing. So if you're going to filter now, you need to filter the spacecraft, not the guys inside it, okay? So LES basically is this. You take the spacecraft, you just toss out some stuff, and then you are left with something in between. So then you have to account for the things that you toss out from the spacecraft with some other things. Okay, so this umbrella here, it's an additional term in the Navier-Stokes. There are actually a few terms if you do it properly. Okay, this is called the Sutton scale model. Okay, so this is what LES is about. It's about manipulating the equations into giving you something that you can evolve in time, right? Not about taking data and coarsening them and things like that. Okay, you can do the same thing if you do like climate model, but this shifter, what is called there, whatever, it's a little bit different. But okay, questions about that? All right. So a lot of us, they cite this paper from 1963 of Smagolinsky, but it's not really an LES paper. Smagolinsky, this is a very big paper because it's basically the first GCM paper. Smagolinsky was trying to figure out how to do a simulation of the entire atmosphere. He needed something to take energy out of the small scales, and he got influenced by the work of von Neumann and Richtmeier, that they were basically simulating nuclear weapons. And he liked nonlinear viscosities. So this is how Smagolinsky decided to do that. Basically, take the rate of strain tensor, multiply this by itself, and give you some nonlinear viscosity. Actually, it's not a great choice. I know that these days, like some of the die cores, they have like hybrid viscosities and things like that to keep them stable. Then Lilly 67 this is kind of like the first formal derivation of like the 3D model. Bierdoff started doing LES in the 70s. Schumann did this 73 also in parallel, doing this in Europe. And then 74, Leonard was working at Stanford, and Stanford was kind of like talking with NASA Ames. And NASA Ames wanted to they realized that this area of computing and like computational fluid dynamics was becoming significant. So they wanted them to do something so that they can build like their capability. So Leonard was at Stanford working with Felsiger and Reynolds. So Reynolds was actually like what they say is that he was the one that started using this term large-eddy simulation. It was like his invention. The Europeans and maybe some people at NCAR were doing this at the same time without calling it LES. They called it something differently. So 75 is kind of like where the term becomes more popular. And by 77, this is a little bit more, you see this more in the literature. And this is from 77. This is from Clark's PhD thesis. And I just copy-pasted whatever was like in the PDF of his thesis. So Clark says that, hey, look, if you're trying to, have a model of turbulence, and you want to get like the model like the large scales. So large scales means, if you're doing climate modeling or weather, the large scales means basically the clouds, mesoscale organization, like we're going to talk about. I'm not very hopeful. But if you go down to smaller scales, they look more universal. So there's a little bit of a hope for that. So that's what he's saying here. So he's basically providing like one of like the best nice definitions of what large-eddy simulation is and what we should expect in the future. Okay, this is like the first time like text like this appears ever. Like the previous papers I showed you was a little bit, not so clear. Okay, so he says, hey, this is LES, and this is called subgrid scale model. And from then on, basically the engineers took it and they started doing a lot of stuff with LES. And the atmospheric sciences, there's like this paper by Someria, like 76. Again, this was part of like LES doesn't appear in this paper. Again, he's basically using the Dyatlov code from the 70s, where he ran like the channel, and he modified this to do cumulus clouds. And actually, if you look at the equations and everything in the paper, it's basically the same as it is today. Like there is nothing missing. The graphics are 76 graphics, but nothing. It's basically pretty much everything is there. So these days we do this sort of like process level studies where we have this LES and we want to study like clouds, like the ones I showed you before. We want to figure out something about the clouds, or we are using LES as a reference if you want to do parameterization for climate models. I'm going to go quickly through this. I have a couple of slides of how we use LES as a reference. So now we're back into like the more large scale stuff. So you are a climate modeler or a weather modeler, and you cannot resolve like the fine turbulence inside the clouds, right? But you're getting in terms like this one. Basically, this is like the covariance of the temperature. Okay, so you need to model basically this covariance. You need an expression for the covariance, okay? If you go back to like the earlier turbulence modeling from like Prandtl, like in the 20s and things like that, it will tell you, hey, I'm going to take like the gradient of theta in this case, the temperature. I'm going to multiply this with a coefficient. I'm going to call this like eddy viscosity. Problem solved. This works if you are like in engineering flows where you have a lot of shear and there's always gradients of stuff. But when you have convection, you look at the potential temperature profile as you go up, no gradient, right? Big problem. So you need a way to generate. So now the problem, you're looking for covariance. You need to find this covariance that you just threw away because you either filtered or averaged. So you need to recover it, right? This is what the turbulence model does. So you need, and what Prandtl found in the 1920s doesn't work for you. So there's many of ideas about this. One of the ideas, this is some of the stuff that we're currently working on as part of like the CPT, is that, hey, I know that my flow has a structure. It has like these plumes, these updrafts that they go up. So what I'm going to do, I'm going to track these plumes as they go up. Okay, so I'm going to say, hey, the plumes have a different temperature than the mean. Okay, so you have this excess of temperature going up, and then they're going up by this rate m. Okay, so this is a way to generate the covariance that you just threw away, right? So yeah, turbulence modeling is a little bit, you have to do this. If you think about this, it sounds a little bit nuts, right? You throw something away, but then you want it back. Whatever. Okay, so now you want to figure out, say, what is like your temperature in the updraft. So you say, I'm going to start from the ground, and as I go up, I dilute. That's great. Great idea. All of this stuff in reality, they become nasty. Okay, you want to track how much as you go up, you're diluting. Oops, sorry. There is like this equation over here. This epsilon is something that everybody loves, like in the atmospheric sciences, called like the entrainment rate. It's basically like the rate of dilution of these things as they go up, as they kind of like interact with their environment. Okay. This is now, it's like a parameterization. So you're making like now a nonsense of what is like the shape of this as a function of C. This usually comes from, it's not like, something that you just appears, right? there has to be some theory, something in the background that you kind of like work it out into like a nice parabola, like this one here. But this is a simple case. This is a parabola, but you don't know the coefficient. So you know the shape, don't know the coefficient, and then you do this experiment. You try to plot this relationship here. This LES, these dots is basically data from the LES, right? And then this is my parabola, and you say, hey, if I choose this 0.4, works out great. That's where my parabola is. So this was for a long time the state of LES. We were doing LES to basically plot these symbols, these dots over here. Then we pick 0.4. We put this in the parameterization. Everybody's happy with it. I was happy with it for some time now, not so much, because we ran these big LES calculations, and then in the very end, then we would have like terabytes of data. Then they all get condensed into like this one value, 0.4, which I don't find very satisfying. I'm not very satisfied with this these days, but this is another issue. Okay.
Does anyone do like stochastic perturbation of that within a scheme?
Yeah, there's iterations of this where you can have like multiple plumes, and they all are initialized with like some distribution, and they go up like and things like that. So there's all of the variations out there. Okay, so this is so we work a lot with these guys. They're doing this. They need basically reference data. They need something that doing this in the atmosphere outside is very challenging. It's very expensive. You need like 3D measurements. You need to know what your environment is, right? You need to know details about what is like the environment that you're working in. So it's very expensive to do this in the atmosphere. And LES is pretty reliable. It has been like this for a long time. So this is how this problem, this mesoscale organization situation started for us. We said, hey, we're going to give you some reference data for shallow precipitating convection, okay, over the ocean. So we're going to do the LES, do a big domain, figure out everything you want, going to give you the data, write the paper, like leave us alone, right? Well, okay, so after we did the simulation, they got a little bit more interesting. So if you ever saw satellite images, either for weather or climate, clouds have patterns, right? Especially over the ocean. So this organization, in the latest years, it has started to kind of like, get a little bit more, people are interested in it. So there's many papers, I cite some of them here, there's plenty of others. So what we are going to do here, we're going to do something a little bit different. We're going to not just look at the pattern, but we're going to look into like the development, how the pattern grows, okay? There's a couple of like additional questions of like how big the computational size has to be, because these are big stuff, okay? If I grow my domain size, do these things keep growing or they just stay where they are? Things like that. So we are going to use what we call like an idealized case. So this is a case that is based on observations that all of these guys did outside in the trades, okay? So this is sort of like a standard case that everybody runs. It's not weather forecast. Again, it's a little bit idealized. So it's, we'll come back to that a little bit later. Okay, so to be specific about the variability, these are sort of like the images people see these days. So this is very intriguing. They gave them names. This is one of like the most popular papers in this part of the literature. So this pattern is like called sugar, for example. These are like flowers, things like that. The idea here is to kind of like correlate the pattern with the conditions, and the vision is that as the atmosphere is warming or adjusting, the adjustment of conditions, so you can figure out maybe the adjustment of the pattern or the other way around. Okay, so this is kind of like the premise of this.
Is there an idea of like what order effect it is, or what order introduction of bias it is to not account for the organization of convection in climate models versus all of the other sort of things that we do wrong in climate models with clouds or?
Yeah, I think some of the bias that people observe in, right now, like in these shallow convection parameterizations, they come from, not taking into account the pattern, right? Because in the parameterization, unless some deep convection parameterizations, they do have this, they call this like whole pool of, parameterizations or corrections. In shallow convection, like this is not very, very common, at least it's not widely used out there.
But that's really hand wavy, and that's like I have the same question every time I see one of these talks about gravel and fish. It's like, who cares? Why? I mean, yeah, they're pretty pictures, but convince me that this is important for us to study climate.
Okay, I'm not studying fish or flowers, right? Okay, but what I'm studying and what I'm interested at, and this has become popular for two reasons. Like we have plenty of so we have, collected over time a lot of observations, right? So we have a lot of images, and now we have this machine learning, like neural network algorithms that they can classify this in an objective. When I say objective, I mean you let the machine do you take out the human. There's a human involved, but the human kind of like taught the machine how to do this. Then the machine saw the counts, right? So this is, because of this stuff, like you can sort of like classify this. Again, in nature, you don't, there's like in between. And if you look at the classification kind of like parameters, they intermingle. Like there's nothing so clear cut in nature. Okay, like I said, I'm not studying fish or flowers. What I am interested at is there is like this pattern, right? But the pattern didn't start like that. It was something else initially, right? So the boundary layer was in another state, and then it got into this state. So I want to know how fast it will get from one state to the other, right? So this is like the question I'm trying to answer now. And when you go from one state to the other, what does it change? Like if you're like a parameterization person, do you have to worry or do you not have to worry, right? Okay, let's go figure this out. So we're gonna do LES. This is like our model setup. We're gonna do LES over like a box of the atmosphere. Okay, we're gonna do just simple stuff with the LES. This is our turbulence model. We're gonna do warm rain microphysics. This is like a 2-moment bulk, Seifert and Beckering. Nice numerics for transport, and pretty standard stuff with respect to computing. Okay. We're gonna do these experiments now. We're gonna do this LIGO case. It's like a precipitating shallow cumulus case. Again, it's idealized comparison, whatever case you want to call it. Okay. We are going to do 4 simulations at different domain sizes, and the domain size will vary from 40 meters. So these are like squares area of the atmosphere. So this is 40 by 40 kilometers, going all the way up to like about like 320. Okay. The resolution is pretty high. It's like 40 meters. Some of these big runs, like these are the runs become like pretty big if you go to this scale. Just for reference, the internal comparison runs this for about only to 24 hours, and the nominal domain size is only 20 kilometers for the internal comparison. I'm going to give you a little bit of like a spoiler here because I'm not sure if I'm going to get all the way like down to the very end. So 160 kilometers is pretty sufficient. So whenever you see the last two, basically kind of like give the same result with respect to domain size, okay? So we're gonna run for 36 hours. There is no diurnal cycle, anything like that here. We just have convection. And this is over the ocean, so the diurnal cycle is not so slow. It's our cumulus. So we're gonna run from like initialization to 36 hours after initialization. We're going to see let the boundary layer evolve. After about hour 30, the boundary layer gets into kind of like a sort of like a steady state. So things are not evolving anymore. You're just there. You're still drifting a little bit because the way the case is set up, but you're basically after 30 hours, you're basically there.
Surface fluxes?
Surface fluxes, it's whatever like these guys say. It's like they're based on like bulk coefficients. So you take they're interactive.
Yeah, I forget. That's right. She specified the transfer coefficient.
Yeah, it's based on transfer coefficients based on the velocity of like the first level of the surface. But they are interactive. Okay, so something that you guys and we're gonna kind of like start thinking a little bit about here is that I showed you before this this situation. So I said, hey, I have a GCM and I have some I can resolve stuff here, and somewhere here is my LES. So now with these big domains, the LES is kind of like 320 kilometers. You're kind of like having a little bit of like a overlap here. So you're not just sampling a few cumulus, you're basically sampling like a big chunk of what some people call like the mesoscale. So you have some part of these large scale motions, but at the same time, you don't have this part inside the LES because it's periodic. So there is like these things going on that, we need to be, I don't have all the answers today, so I'm here to ask you. These are the things that we need to be thinking about. All right, so validation. So again, there is nothing exact that you can validate against, but we usually do three things. Because this is based on observations, there is data about what is like the cloud cover, how deep is the boundary layer, how the clouds look in reality, what is their structures, things like that. We run the LES, and there is, if you read the papers, that if you read our papers, like there's like citations to these guys here that they say, what these quantities are. So we check that we're within the range of the observations of the atmosphere, right? So you expect this shallow cumulus that they go like 3 kilometers deep. We check that we go up to like 3 kilometers somewhere there. Okay. So we also check for grid convergence. So we run different grid resolutions. Here we run 20, 40, 80. We're plotting here liquid water path for cloud, rainwater path, surface precipitate. This is TK. 40 meters is good enough. It agrees mostly with for all of the stuff with the 20 meters. So we're going to stay at 40 because it's much cheaper than running 20. So, and then if you're a modeler, you know your configuration that gives you the most accurate results, right? So we choose the like the high quality advection scheme. We go like fourth order. We actually do these simulations in the frame of reference moving with the mean wind because it reduces some of the error in the model and things like that.
Can I ask about the surface precip rate?
Yeah.
We see figures like that a lot. Where, for instance, if we look at the rainwater path on the upper right,
Yeah.
So do you think you would be sensitive to domain size as well here? Okay.
Yeah,
yeah, and then so when we see big oscillations, we think, oh, our domain size isn't really big enough. And then, but then on the lower left, at 20 meters, you have this high surface precip rates, and then at 40 they're low, and then at 80 they're high again. So,
yeah, I think this is a domain size thing because give me 2 minutes.
Yeah,
I have more figures about this. This is like the domain size.
Yeah, this stuff is tricky.
It's tricky, yeah. So this domain size is 20 meters. It's 20 kilometers,
yeah.
which is it's very, very small. Okay, domain size. Okay, so these are like our 4 runs. So this is the big domain size. So this big box is 327 kilometers in each side, right? So this is the 40 by 40. And then you go up each time, doubling. Okay, so this is like the big domain size. So there is like this big stuff happening. These are basically these cloud arcs, cold pools. Basically, what happens as precipitation falls below cloud base, evaporates, cools the atmosphere, suppresses convection for a little bit, like in this area. So this becomes sort of like a gravity current kind of situation. But it's not really that because you have convection kind of like at the leading edge. And you have this these areas that you see here, this is like basically like stratiform that just was what they trained from the cumulus. But you see, there's like these big things happening. So if you're this is 40 by 40. The previous slide was 20 by 20, so it was 1/4 of that. So things don't fit into like the small domain, okay? And only like the two largest simulations they have, they show these cold pools. And if you, I don't know, if you kind of like stretch it a little bit here, you can see that, you know, like the distance, like this distance and these distances over here, they're kind of like the same. So if you're over here, like at this kind of like range of things, like 160 kilometers, you're basically kind of like, you have reached the destination that you want to be, okay? The other thing I wanted to say is that if you look at these old boundary layer papers, they have like this fair weather cumulus and things like that, and everything is like popcorn cloud. You know, boundary layers are not always like that boring. You can get interesting stuff even in boundary layers. Okay, so this is the question Anne was asking. Okay, so these are like the full domains. So this is now time going up to hour 36. This is surface precipitate. Okay, this yellowish orangey thing and the black are basically like the two high resolution ones. Some of the big oscillations that you see from like the smaller domains, they got averaged out a little bit. There's still big things happening. So when you get one of these big structures firing off, it rains a lot, so it shows up in the signal. But if you look at the black and the yellowish orangey line, you see in most of the cases they're pretty close. So 160 and 320 kilometers, they don't make a big difference. What I also did not say, but we did, the bigger one here, we did not run like from the beginning. Basically, we took this one, the black over here, like at hour 16, and then we repeated it 4 times. We added some like random perturbation so that we randomize it a little bit, and then we let it go because these simulations are very expensive. It's it's a big grid. We are not going to spend computing time just running like 16 hours of fair weather like cumulus in these big domains. So that's why all the orangey lines, they start from hour 16, right? The other thing, okay, so the first interesting thing we noted is that as the domain size becomes bigger, this is cloud top. We see clouds reaching higher and higher and higher, and we wanted to check that is this like something that we need to worry about? Is this happening a lot? What is like the frequency of this thing? So we this line here that you see, this basically where like the inversion is. So for us, inversion is the height of the maximum theta gradient. Okay, so it's hour 16. These are the 3 smaller domains. They basically all agree, but after you get into like the more organization and the more vigorous convection, at basically hour 22, the bigger domains, they have like this small tail here. So sometimes within this very vast domain, there is a cloud that kind of like wants to overshoot a little bit and go up. And this is what is kind of like what you see here. You see like, if you look at this, it looks very kind of like very severe, but this occurrence of like very, very high cloud, this occurrence of very, very high cloud, they are not so frequent. Okay. And now we're going to answer the question we started with. Okay, so this is sort of like not the biggest domain, but kind of like the 160. Okay, so what happens is that in the beginning you have a state like this, right? You cannot see all the little clouds here; they're too small for the pixels of the screen. But you can imagine that they are all there. Okay, you start from states like that are kind of like this, and then you get these structures, these cold pools and the cloud arcs, that they start growing. Okay, so this is what we're here to study. Well, that's the question we asked ourselves in the beginning. What is like how fast does this stuff grow? Right? So if you're like outside in the real atmosphere, how fast are you kind of like transitioning from one regime to the other, right? Is it, like in 10 minutes within a time step of your climate model? Does it take hours? Is it like something that, so what is like the growth rate of these guys here? Okay, so this is, again, I think this is like a small section of like the big domain, and you can see that how this kind of like cold pools and cloud arcs, they kind of like move around and they spread. So we are here. So the question is, not how fast this guy is moving, it's how fast it is spreading radially. Okay, this is the question that we're trying to pose here. Okay, if you're doing this in turbulence, and if you are doing like this in an engineering flow, what you have to do to extract the large scale characteristic turbulence scale, right? So what you have to do, you construct a 2-point correlation, and then you integrate that, and then what you're going to get is like a length scale, and that is your characteristic large scale of the flow, right? Then you put that into your, in a Reynolds number, and you tell me what the Reynolds number is. When we tried this here, there was a little bit of a problem. So what you see here, so the x-axis is distance, okay, and this is the correlation. So this is the correlation for the zonal wind. This is the correlation for the vertical velocity. This is the correlation for moisture. Okay, so if you're at hour 16, before the organization really developed, is what you expect from the standard like turbulence textbook. If you go in one of like the oldish turbulence textbooks, they will tell you, hey, the correlation has to be, this is like the normalized correlation. So if you are at 0, you're at 1, you're completely correlated with yourself. As you go out in distance, you're going to trail off, and then in the end, you go to 0. Depending on, if you're along the direction of your vector or the other one, you can go negative or not. Like these are like classical turbulence theory stuff. The problem here was that this is hour 16 in our land before organization developed. This is kind of like the medium state, and this is after you get these big cold pools. So what you observe, and these different lines are different heights within the boundary layer. After organization developed, except the vertical velocity, the other curves did not go to 0. They were just hanging out there like for large distances. Okay. The only curve that always went to 0 no matter what is the vertical velocity. Okay, so keep this in mind. And the scale here is different. So this is 0, 1, 2. This is 0, and this is 80. Okay, so the vertical velocity, no matter what's going on, it just drops off to 0 really fast. Okay, I think this is the same, not problem, the same phenomenon they see if you read some of the literature on like this big, the latest big campaigns on like trade wind boundary layers. They see this sort of like local like circulations happening in the boundary layer, and this is, I think, this is what the same thing we see in sort of this fake idealized LES. You have these large scale motions that are kind of like meandering inside our big box. Okay, so we need to do something different. Okay, so what we did is this. So you take now the spectra. Oops. So this is I converted wave number to length scale. So this is a big domain. So these are decades. So if you look at hour 16, before organization developed, so there is kind of like a power law here, and then this is also interesting. It doesn't want to let it flat out, but it just has a little bit of a slope here, and there's a little bit of a bump here. So this is like the regular spectrum, normalized. This is the premultiplied spectrum. I multiply with the wave number. So if you do that, you're gonna get spectra that have like a bump somewhere. Okay. So if you do the premultiplied spectra and you get bumps, this tells you where the energy is concentrated at, right? So what I'm basically saying here is that if I am getting into situations that they look like this, I have this big guy here, and it has a lot of stuff going on at a certain diameter or radius, I need to pick up this signature on the spectra. And if you do this before organization develops, the spectra will look like this, single bump, where the energy is concentrated at. If you look at not the premultiplied, but the regular one, it doesn't, it's very inconspicuous. While organization develops, and after it developed, the spectra developed multiple bumps now. So you have like the smaller one, but then over here, you get a little bit of stuff right here, okay? So with looking at these bumps, I mean, I can just go and objectively now figure out where the maxima are. I can go and make these plots. So for each of the variables I have here like the black dots is zonal wind, and the open symbols is meridional wind. This is vertical velocity. This is temperature, and this is humidity. Okay? Basically, total water mixing ratio. So if you track this in time, by hour 16, nothing is going on. It's just like scattered cumulus. But after this organization develops, you are getting multiple peaks in the spectra. Sometimes we detect 3 of them. Okay, and this is a log scale so that everything shows up here. You can kind of like pick up this this growth rate, right? And actually, these symbols here, these squares, we actually went and we measured, the diameter of like the cold pools, right? So the squares is actually like the radius of the cold pools, and the growth rate, it's a little bit, we got a little bit lucky that they actually match in value, but what we're looking to match is basically like the slope. So this is, and if you look at how much this stuff are growing, this new larger length scale, the growth rate is about 3 kilometers per hour. So you have these big structures that are growing now in horizontal size, and our answer here, at least for this case, these guys grow between 3 and 4 kilometers per hour. The very interesting thing is that, again, vertical velocity only has like a single peak, the spectra. Okay, it doesn't develop any other peaks and things like that. It just has like the small scale, and the scale is about like 1 kilometer, and that's it. Whereas these bigger ones, they do have like the small scale about like 1 kilometer or 2, but there's like this additional length scale that develops in the flow, that this is about like 80 to 100 kilometers after it has like reached its kind of like steady state. How am I doing with time?
I was actually just going to ask you to pause. We're right up at 2 p.m.
You are right at the.
If we can just pause,
Let's-
we can go late, but I want to give people a chance if
Yeah.
they have a meeting next to just ask any questions really quickly, and then we can go over time.
You might go into this, but the 3 to 4 kilometers per hour, the growth rate of the hopeful edge, I think that's what we'll talk about a little bit. Is that, do you know if that's in alignment with like standard, gravity current, density current theory?
No,
it's not.
It's not. There is like papers like this one, for example,
Right.
that they look at gravity currents,
Right.
and the growth rate that we see here is linear with time, so it has a constant slope. These are the same plots. I just plot like a linear y-axis here. Our growth rate is linear, so it's like 3 kilometers per hour. It just goes like that until it reaches the big size. If you look at the gravity current theory, the growth rate is a fractional power of time. So it grows and then the growth slows down. And there's a big difference here. There is the gravity current is just like buoyancy that is spreading out. Here you have convection that is sort of like shooting up from like the leading edge of this thing, and the convection kind of like propagates along the way.
Are there questions online?
No, there's no questions in the chat. If you do need to log off and you're online, please feel free to put them in the chat now. And if you need to head to your next meeting, please
Yeah,
feel
yeah,
free to do so. But if you want to keep going, I think we have the room still. So.
Yeah, done. Let's spend a few more minutes, and
I think I'm pretty much done, actually.
Okay, well, let's spend it. Maybe we'll go. That sounds good, and maybe there's a summary slide. I have a question about this figure, really
I'll
quickly.
show you my summary slide, and then...
Yes, that sounds good.
Okay, so the important stuff was like at the very end, right? So we asked this question of, how fast this organization happens, right? And for at least for this case, what we find is about 3 to 4 kilometers per hour. This is sort of like the rate of change. It grows to about, in this case, 80 to 100 kilometers, and it just stays there. It just doesn't grow anymore. After you run this for even to hour 36. Domain size, 160 kilometers, is good enough for this case.
Wait, did you do this domain organization change of time with the larger grid too?
Yeah.
And it stops at the same scale.
Yeah, it's actually here. So the orangey symbols is with the bigger domain. So they don't grow anymore. They just kind of like, they grow and then they just stay there. The very interesting thing is that the vertical velocity, it doesn't show this kind of like the large scale organization. So I think this is what saves the day in the end for other parameterizations, because what we see is that the individual kind of like convective elements, just by themselves, they don't change. They kind of like get a little bit like rearranged in the horizontal so that they kind of like work together maybe into these arcs, things like that. But just by themselves, if you look at the vertical velocity statistics, if you look at variances or the length scale, like right here, it does grow a little bit, but it's not growing that fast. It doesn't develop any new large length scales. It just stays the way it is.
Do you think that length scale is related to the boundary layer depth?
Yeah, so the smaller one, like the small length scale, it is basically like the one that has to do with the thermals and the local convection, and that is linked with the depth, right? It's like the relevant length scale for that.
Yeah. Do you have a question?
Yeah, so much seems dependent on precipitation formation. Does it matter how you treat aerosol in your simulation?
So this, yeah, I think this is a question I get asked all the time. Every time somebody's, I don't know the answer to this. Like we haven't changed the aerosol.
What do you use?
So the scheme as we have it now, it just uses like a constant value for CCN. We just use the nominal value for the case, and we just run. We don't have interactive aerosol in the model, so we don't know the answer to that. But if you change the precipitation in any, we have done tests without precipitation. You can turn it off, right? You don't get the organization. The boundary layer stays basically like half a cumulus. The cumulus grows a little bit in time, but you don't get the big stuff. I don't know about that.
So there could be another aerosol timescale, I guess, though. A consumption timescale.
It could be, yeah.
Restoration, yeah. All right. Thanks so much, George.
One more.
Oh, one more. Sorry.
You said the vertical wind spectrum didn't change.
Yeah, it doesn't change. So if we so these are our vertical velocity spectra over here, and this is our 24, 30, 36, and I'm plotting like all 4 domain sizes on top of each other here, just like single peak. It doesn't change.
What happened to the horizontal wind?
The horizontal wind changes. So the horizontal wind is this guy over here. It changes a lot. Like that's it develops multiple peaks, and it has the tendency in kind of like developing this sort of like large scale horizontal motions. This is it's I don't this is a periodic domain. Everything has to be in this box, right? The conditions are homogeneous. So this is, in reality, there is large-scale shear that takes things and is kind of like stretching them around or spinning them around and things like that. This part is missing here. So whenever we start talking about mesoscale, this is a little bit of a fake mesoscale. It's a homogeneously, it's a planet where the atmosphere doesn't have any large-scale forcing, basically, right? It's like the geowind is always homogeneous over this like big piece of atmosphere, which is it's not realistic as you go bigger and bigger.
But it's very useful for parametrization development.
Well, this is how we got into this this thing. We said, we're going to do a big domain. We're going to figure out everything you guys need us to do, and then it's like tell us what to learn next, and then it got a little bit more interesting.
Right, so we do have one, maybe make this be the last question, from Ron in the chat. He said, why is the cloud top height PDF bimodal? What determines the height of the peak that is below the inversion and within the PDF?
Right. Okay. So this peak here is basically thermals. They just shoot up a little bit above like LCL. They condense, so you get this puffy cumulus. Right, this peak here is basically because of stratiform cloud. So the cumulus go all the way up to the inversion, then they hit the inversion and then they detrain. So they create this kind of like splatter liquid around near the inversion.
And you've got a Beer's law long wave, so they can sustain themselves, right?
No, we don't have any.
Oh, I'm sure that specification. I'm quite sure that specification had some Beer's law kind of stuff down.
Maybe
we can look.
maybe we can. Yeah,
It's been a long time since I ran that case. Or she said it's the last question.
Well, we can discuss if you guys want. I know John has to log off.
I only go when
We can
it's like over
continue
time
this
here. So
Andy, let's discuss this in the office. It is an interesting question because then you're moving into more of a stratiform regime, which is more handled by your stratiform scheme and your model. So it's we can continue to discuss. So thank you so much, George. Too.
yeah, thank you. Sorry for going a little bit.
No,
like
I'm
over
sorry I
time
didn't give
here.
you any warning. I was so enwrapped. It's great to be here.
All right, thank you. We can just get
Thank you.
And Ron said thank you for the explanation. PDF.